Welcome to this lecture number 16 of the course Computational Hydraulics. We are in module 2 numerical methods, and in this particular lecture I will be covering unit 12 finite volume method conservation law. What is the learning objective for this particular unit? At the end of this unit, students will be able to discretize the conservation laws using finite volume method. We have seen this form of equation during our finite volume discretization. This is one dimensional scalar conservation law, where phi is the general scalar variable. F phi is the flux function and S phi is the source term for this one. Now, if we write the conservation laws in the form of vector, then for phi 1 to phi m, these are scalar variables, and f phi 1 to f phi m, these are corresponding flux functions, and s phi 1 to s phi m, these are actually source seeing terms. So, we can write it in this vector format. Here this comma t means we are differentiating this thing with respect to t. This is phi, this means this is phi comma t. Similarly, for d by dx, f phi, we can write f phi comma x. This is a short notation for derivatives. So, with this form we can start our problem. We can define Jacobian of the flux function, where this A phi matrix is actually del f phi del phi, and individually these are terms, and in this case we can define our thing. If we look back to our finite difference lecture, then we can see that d phi by dt plus del phi f by del x, del phi and del phi by del x, this term was there for single variable. Now, if we consider the same thing for a complete system, then we will have this Jacobian matrix. In place of single derivative, we will have full Jacobian matrix here. Now, we have seen that that derivative in one dimensional case dictates the nature of the solution. In this case, we can have the non-conservative form. Similar way, this phi t is again derivative with respect to t, a phi is our Jacobian flux function, and phi x again vector of phi with derivative with respect to x. This is modified sourcing function. Now, in this case we can find out the eigenvalues of this Jacobian matrix from characteristic polynomial. So, if A is the matrix, I is identity matrix, only diagonal terms will be there, other side it will be 0, and lambda is some characteristic value we can use here, and eigenvalues provide information regarding speed of propagation, and propagation of information from one side to another side. For hyperbolic system, at a point x t, if Jacobian matrix has m real eigenvalues, m right eigenvectors are linearly independent, we call it as hyperbolic system, and in this case we call it strictly a hyperbolic if all eigenvalues are distinct in nature. Let us consider our one dimensional conservation law. We have general P cell, E cell, and W cell here for some interior node. Now, for this one we can define our finite volume method. It is with space time discretization. The first term is for temporal derivative, second term for the spatial derivative of the flux function, and last one is sourcing term. And interestingly, we can see that this omega p refers to the P cell. That means for that elemental volume we are considering this integration, and for T2 T plus delta T, or we can say that time starting from Tn to Tn plus 1, we are discretizing this thing. So, we are taking the integration for that level. We have considered this case P cell. So, P cell is running from x w, that is face w to E, this is P cell. Now, for derivative here we can replace the limits or integral limits x w to x e for all the cases. Now, if we simplify this one, we can write it for discretized form, and here this is del t t plus delta t and t level. In this case we have taken discretization in terms of space values. So, E and W, in this case we have outside only spatial integral, this is temporal one, this is space time, we have not divided this thing. Let us define the averaged value of phi p n, that means at any time level n, cell averaged value we can define like this. And numerical flux function can be written because we have discretized in terms of space, but still the temporal integration is there from t to t plus delta t level. So, for east phase we need to consider p cell and e cell values. For w phase we need to consider w cell and p cell value. Depending on that we can calculate the flux function. Final form of the discretization, if we simply replace these terms, and of course, in this case we are not considering S phi because discretization of S phi depends on its functional form and more or less that is constant. So, we will not consider the discretization at this stage. So, let us concentrate on the first temporal derivative and then spatial derivatives of the flux function. So, this is a final form, but still we need to calculate what will be the value of this flux functions. Riemannian problem, this is conservative form. We already know that we have p cell, w cell, e cell. Now, at each cell there will be different cell averaged values. So, Riemannian problem or Riemann problem essentially comes at the interface, where let us say we are considering this east phase. If x is on the right side, so this is phi e n, on the left side we have phi p n. If it is on the left side, it is phi p n. So, as essentially there is discontinuity at this level. So, this problem is called as Riemann problem. Now, in this case, first hand approximation of the flux function can be averaged flux values from both the cells. So, at east phase we can consider that phi p for flux and phi e for flux, and we can take average, and west side also we are taking average of flux values of w and p. Now, this is first hand approximation. If we consider our numerical discretization, then only flux value for the east phase and west phase will be required for this calculation, and 2 is coming here. Now, let us consider the simplest form of the flux, where A is constant, phi is our general scalar variable. Then we can write our final form of the discretization using finite volume technique as A delta t 2 delta x phi e minus w. We can also represent it in terms of I j or I plus 1, I minus 1. If you have P cell, then at the center we can consider it as I, on the left side it is I minus 1, on the right side we have I plus 1. So, for each cell this is I plus 1 and west cell we have I minus 1, and A delta t by 2 delta x, this is coming as a constant. Now, we need to see whether this discretization is stable or not. Like our finite difference technique, we can use our error equation. Error equation, we are writing it in terms of epsilon I n plus 1 var epsilon, and this is var epsilon I n, and this term is constant. Now, for this one we can define our terms as A delta t by delta x. So, this is CR by 2, and as per our convention, we can directly write it as e to the power square root of minus 1 phi var phi x. Actually, we have seen that this epsilon I n, this is A n, and e to the power minus 1 I var phi x in this case. So, for var phi this var epsilon I plus 1, this will be n square root minus 1 I plus 1 phi minus n. So, we can just simplify this one and get 1 minus square root of minus 1 CR our sine var phi x, and in this case we can write our g or growth factor, which is g into g star, which is conjugate complex number. So, this is minus, this will be plus. So, always 1 plus CR square sine square var phi x. In this case, it is clear that 1 plus some quantity. So, CR is always positive because square term is there, sine square is again positive. So, 1 plus some positive term will be always greater than 1. So, this scheme is unstable scheme. So, this approximation or first hand approximation is not appropriate. This is unstable scheme. So, Lax-Friedrich scheme, in that one this same type of flux, average flux is used, but one extra term is added here, which is difference between east and our central P cell, and west phase this is P minus W. So, final form is averaged value of W and E instead of phi P n. In previous case we have seen that discretization was with phi P n value, but in this case we are taking average of W and E. Now, with this again we can write it in I minus 1, I plus 1 format. If we see our actual equation, then this is our actual equation, but virtually what we are doing, we are adding some extra second order diffusion term here in the Lax-Friedrich scheme for stabilization. So, in this case this diffusive flux, we can say that this is some beta into phi P minus phi W for west phase. So, this extra term is added for stabilization of the scheme, which is equivalent to adding one extra term on the right hand side. So, if we check the stability of this scheme, again this is averaged value. So, if we check our stability for this case, the CR is defined with A delta T by delta x. We can get this cos var phi x minus square root of minus 1 CR sin var phi x, and if we write our growth factor, again that is G into G star, which is conjugate complex number. So, in this case we are getting cos square var phi plus CR square plus sin square var phi. So, we can rewrite this 1 minus sin square var phi x plus CR square sin square var phi x, and if we rewrite this, we can write it like this, and in this case scheme is stable if CR is less than 1. If in this particular case, if we have 1 minus some quantity, if CR is greater than 1, then this quantity will be negative, and negative negative this will be positive. So, 1 plus some quantity. In extreme case, if we consider that sin var phi square, this is equal to 1, this is extreme case, that sin phi x this equals to 1. So, this comes as 1 minus C r square. This means that this is C r square. So, obviously, this should be less than 1 for such stable scheme. Another extreme is sin var phi x square, this term is 0. So, then obviously, that is neutrally stable. So, we can see that depending on the approximate form of the flux or numerical flux function, we are getting stable or unstable schemes. In the next lecture, we will see another kind of approximation for this flux function. Thank you.